Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Buhari Imran, and today I will start to present my part by explaining about the concurrent programming. So, the concept of concurrency is in this robotic is to allow robot to execute multiple tasks or processes simply at the same time. Well, traditionally, sequential programming model where tasks run one after another is inadequate for robotics. It will force the robot to halt its movement to check sensor, make it unresponsive. Therefore, concurrency resolves this by enabling functions like obstacle detection, line following, and signaling to operate in parallel, which is essential for the robot's efficiency in real-time responsive. So in that concurrency, there is also a task management, which is handled by a microcontroller operating system, which is use a fixed priority scheduling model. This model ensure the critical tasks are executed without a delay. In with each task in the system is designed specific with specific priority level based on its importance to the robot operation. So for the task hierarchy, it will start with the highest task, which is task start. This task, the sole function of this task is to initialize system and create all other application tasks. It is given highest priority to ensure a correct and interruptible system setup. Then priority number two, check collision. This task handle obstacle detection via the proximity sensor. Its high priority is critical for safety, as it allows robot to react immediately to the obstruction or any obstacle, preempting less urgent function. And next priority is control motor. So for the control motor, this directly control the motor output. It requires high priority to ensure the commands from the navigation logic are translated into smooth and immediate physical movement. Next is navigation. This is a primarily navigation task. It processes data from the line sensor to calculate requires motor speed, which is essential. It priority to set below motor control and collision detection to ensure that physical action and safety checks are always serviced. Next, the lowest priority is the light handler. So this is mostly on controlling the LED to respond to the light signal, and is a non-essential function for navigation for safety. So it was assigned to the lowest priority. So for the software architecture that built for this RoboKar is built around a centralized data structure. This global structure named MyRobot contains all critical state variables, including motor speed and obstacle status. This design This design facilitates efficient inter-task communication. For example, the navigation task writes desired speed to the structure, and the control motor task read this value to act upon them. This shared approach offers simplicity and performance, but introduces a potential for data corruption if multiple tasks write data simultaneously. While more complex projects will use protective mechanisms like multiplexers or semaphores, these projects relies on the deterministic nature of the fixed priority scheduler to manage access in the controller manner, making a deliberate trade-off of the simplicity in this specific context. In summary, the combination of concurrent tasks, strict priority-based scheduling, and a centralized data structure allow the RoboKar to perform complex and real-time navigation tasks in a smooth and predictable manner. That's all for me. Thank you.
So next, I will explain the software development process for this project. So for the environment, we use two main tools or coding environment for this project. So firstly, we are using the AVR Studio. It is for low level embed C development, and it is suitable for the microcontroller based system like this RoboKar project. And also we are using Arduino IDE. So it is for the complementary tools for prototyping and testing simpler function. Now you can see this is the AVR Studio. I'm opening the project, and this is the code for the project. So next, for the version control management, so what we do here is that we didn't use any tools like Git or anything to track the version control, but we just treat each of the version by looking at the milestone. So for example, in version 1, we just have basic navigation function and obstacle detection. But in version 2, which is the current version, we have an improved version of navigation. So it has more, it has full navigation, and also it has better handling and more checkpoints. So that's how we manage the version control for this project. So in this project, we use concurrent tasks, which mean that multiple actions can run at the same time. So how we achieve this is that we use UCOS2, which is an operating system that allows us to create separate tasks for each function. So in here, how we implemented them is that we use OS task create function here. So each create task, we have their own priority. So in here, you can see that check collision task has the number 2, the second. So the smaller number, the highest the priority. So check collision will be the first priority, then second, motor and navigation. So here means that if the car detect any obstacle in front of it, so check collision task will be running first.
They have a counter. They what is right? What from start to
In the robo sample code, initially we are importing the kernel as well as the hull-robo.h. The hull-robo contains the methods or the functions that we need in order to complete the task. It provides all the functions such as the robo setup, the motor speed, as well as functions related to the sensors such as light, proxy, as well as line. It also provides the OS ticks in it, as well as other helper functions, including declarations of motors, such as the right motor or left motor, as well as the direction, as well as speed. Moving back to the code. So initially we are setting the priority of each task. So the task start has the highest priority, as well as the check collide, which is the second priority, followed by the control motor, which has third priority, and finally the navig priority. Once the priorities have been set, we first declare it in the task start function. The task start initializes the timer and calls all the functions in a concurrent manner with the priorities set. Once the functions have been called, it runs the robo honk, which sounds a horn, as well as waits for the go press, which means to press the button on the RoboKar, which makes it to start moving. And the OS start calls all the prioritized functions in a concurrent manner. In the navig function, here we are setting the low speed, medium speed, and the high speed. We're declaring the initial variables such as the line value as well as the counters and the check to see which checkpoint we have reached. And it runs a loop where in every loop it checks whether the line sensor has a value, and then it checks the state of my robot, which had 3 states. The first one is the obstacle, as well as the left speed, as well as the right speed. So after checking for the obstacle, if it sees that, it is expected to go back or in reverse for 500 milliseconds, And then if there is a blockade, that means it has reached the L2 part of the track. And this also means we have reached the checkpoint at C. This increments, or we set the counter of the checkpoint to 3, which represents the 3 in the character. Then it reverses back for 500 milliseconds, then makes a right turn, and it goes straight. And if there are no obstacles, it checks if the RoboLight sensor is greater than 80. That means it has reached L1. And then it turns on the LED and blinks for 250 milliseconds, then it turns off. And it does it twice. Once the checkpoint counter is at C and the line value is 7 and it didn't reach checkpoint D yet, this means it has reached checkpoint D at that point. Then it makes a sharp left to enter the circle, and it follows a circular path where it goes through the track in an alternate S shape. Once the circle has been completed, it has now reached at checkpoint E. Once from checkpoint E to F, there is a square box. So the RoboKar now has to detect if after reaching checkpoint D, if the checkpoint E has reached, then it uses the square track state to see if the value is 0, then it makes a sharp right turn. Then if it's 1, then it makes a sharp left turn. And if it is 2, then it makes a final right turn. This helps it to go first straight, then make a right, then a left, and then a right. And finally it has reached the final checkpoint and it will now stop. If all the previous conditions have not been met, it just checks the line value at that given point in time. And if the line value is checked from a value of 0 to 7, if it is 0, that means it has gone off track and it is expected to reverse. Here we are setting the left speed and right speed to negative values so that it goes in reverse direction. For case 1, it makes a slight right of the line where we set the robot's right speed and left speed to a smaller amount. If it is 2, that means it is close to the right, so we make a slightly right adjustment. When the value is 3, that means it is still on the line and it is expected to just go straight. And here we are setting the left speed and right speed to equal values so that the direction does not change. When it is 4, it is close to the left, so we make a slightly left adjustment by reducing the left speed and increasing the right speed. And when it is 5, it makes a slightly left turn by increasing the right speed and reducing the left speed. When it is 6, it makes a sharp left turn by greatly increasing the right speed and reducing the left speed to a small amount. And finally, for checkpoints, the value is always 7. And when it is 7, it is expected to just go straight. This concludes my explanation for the code of RoboKar. Thank you. For the RoboKar testing and performance analysis, the robot was placed on a marked blackline track with intersections, curves, and event zones, which included obstacles as well as light sources. We measured the task execution rates, the time between the sensor stimulus and actuator response, as well as the task preemption behavior under full load. In the code, the OS time delay HMSM configured the task periods, which was verified by toggling the onboard LEDs. The task timing table shows the configuration and the measured timing during full load execution. Initially, the first priority was set for task start, which had the function for the heart rate of the system. which enable the LEDs. The check collision has the second priority, which had a period of 10 milliseconds. Its task was to detect obstacles and trigger the honk. The expected response time was expected to be less than 10 milliseconds, and our calculated actual response time was below that. The control motors with the third priority also had a period of 10 milliseconds. Its task was to update the motor speed and had an expected actual response time below 10 milliseconds. The navic function or the navic task had the fourth priority with the 10 millisecond period, and its task was to read the line sensor and navigate. Its actual response time was about 12 milliseconds, which is similar to the expected response time. Finally, the least priority for light handler, which had a mean time period of 10 milliseconds, that detected light and triggered the LED or honk. It also had an actual response time of about 10 to 11 milliseconds. The following shows the timing diagram, which illustrates how the RoboKar's tasks run concurrently under the control of the micro C or OS2 real-time operating system. This diagram shows that there were no deadline misses for the time critical task. The check collision executes within the highest frequency and lowest latency, and the lower priority tasks such as the navic or light handler still operate within the acceptable bounds even under heavy load, such as the line, light, and obstacle.
السلام عليكم ورحمة الله وبركاته. I'm Musab Mudathir Taib, and I will be demonstrating the final system integration. And here, as you can see, in the game performance for the RoboKar, we have our complete track setups with all the checkpoints that our robot need to navigate. Okay, for the hardware interface explanation, I will be let me explain the hardware abstraction layer. So the interface without our OS2, that the Concurrent software, our RoboKar is actually equipped with three main sensors. So, okay, firstly, we have inferred line sensor arrays underneath the robot for the line detection. This provides the values from 0 to 7 that our navigation task process every 10 milliseconds. Okay, secondly, we have this proximity sensors that in the front, so it will detect the obstacles, specifically the cube at the checkpoint L2. Our check collision task mentors this with the highest priority, which is at 2. And thirdly, we have the light sensor on the top, detects the bright light that signal at checkpoint L1. So the light handler task process this input and have the values. For outputs, we have the motor driver's control, left and right wheels, speed, and LEDs for the visual feedbacks during the checkpoints, which is, you can see it here. Okay, now let me show you how our 5 concurrent tasks work together in real time. So in the mentoring screen, you can see here the task with the priority number 1, manage the system heartbeats, uh, check collision, and priority number 2, handle obstacle detection, control motors at priority number 3, update motor speed, and navigate priority number 4. And following the line, so the light 100 at priority number 5, which is light detection. Okay, now let me show you our system performance against our design specification during that run. Our time analysis shows. So in the table, you can say check collision maintain a 9 millisecond average response time, well within 10 millisecond requirement. Control motors achieve exactly 10 milliseconds periods. Most importantly, no deadline misses occurred during the entire run. So even during the most complex navigation phases, the circle and square sections, our priority based on scheduling ensure that safety critical tasks like obstacle detection, maintain the timing requirements, and everything together. This demonstration proved that our uh, COS2 based on concurrent design successfully integrates the hardware sensors and real-time processing and motor control into uh, good an autonomous navigation system. The robot completed all the checkpoints while maintaining a real-time performance requirement based on that.
Lastly, is the conclusion. So before we go to the conclusion, I'm going to talk about the game day. So the RoboKar game day was held on 24th of June, Tuesday, at the N28 Faculty of Computing Student Lodge. So during the time, our RoboKar facing a several issue, which is one of it is inability to upload our code during the competition, which make our RoboKar unable to complete the full course. So this incident underscore invaluable lesson. So the experience, despite its setback, uh, it enhanced our understanding for a real-time software application and the complexity of the robotic in dynamic environment. So it broadened our insight into a real-world technologies and their essential role in practice problem and solving. So this hands-on application was crucial in solidifying our grasp of theoretical concept. So in conclusion, the RoboKar project demonstrate how a small mobile robot can achieve a reliable real-time autonomous using these COs through a fixed priorities multitasking. The robot meet all timing requirements while handling line following obstacle avoidance, checkpoint event, and comparison with ROS-based platform highlight the trade-off between hard real-time control and highest level flexible feature work, including adding simulation richer sensor and migrate middleware like ROS in the future for this paper. Hopefully, after this, we can improve our RoboKar. Thank you.